Have you ever wondered how are your classmates solving integrals using partial fractions? What does partial fraction expansion even mean? Have you lost all hope for your next Calc 2 exam? Well, if you can relate to any of these comments, then this is the video for you. I'm the Electric Tutor, and in this set of videos I'm going to show you what partial fractions are and how to apply that to integrals. So let's get started. Partial fraction expansion is taking a big rational function and decomposing it and splitting it into smaller fractions. It is essentially the opposite operation of when you add or subtract fractions with different denominators. So in here we're going to go backwards, and in particular for Calculus 2 this is a very useful technique if the rational function you're given cannot be solved directly or with u substitution. When you expand a rational function, there's basically two cases you need to be aware of. Looking at the denominator can be either a linear term, which is what we see here in the form ax plus b, where a is a coefficient and b is a constant. The second case is when we face what's called an irreducible quadratic, which means it is a quadratic expression which cannot be factored any further. I mean, technically you can using complex numbers. We're not using complex numbers in this course, so for us it is irreducible, where a and b are coefficients and c is a constant. Now n is a positive integer power larger than 1, because if n is 1, then the fraction cannot be decomposed into smaller fractions. It has to be 2 or higher in order for us to do this. So when we have a linear denominator, what we do is we split it into different fractions, and the amount of fractions depends on n. So for example, if I have something over, say, 2x plus 3, which is a linear term, then this is as simple as it gets, and you can probably solve this using u substitution. But what if this denominator is raised to like the fifth power, and let's say you cannot solve it with u sub? I mean, you can probably do it too, but what if you want to expand this? Well, the way you do this is you're going to need the 2x plus 3 5 times. So the first one is going to be raised to the first power, which is implicit. We don't really write it. And then you need a 2x plus 3 squared, and then a 2x plus 3 cubed, and so on and so forth until you reach to the last one. Okay, so there's going to be n amount of smaller fractions. What happens with the numerator? Well, we still don't know the constants or numbers that go there, so we need to place sort of placeholder variables until we find what those values are. And typically people put either a sub 1, a sub 2, so on and so forth, or just a, b, c, d in capital letters. I always go with a, b, c, d, etc. And then the next step would obviously be to find out what those variables are. Now for the second case, when we are faced with an irreducible quadratic, we do the same thing on the denominator, but with the numerator it's going to be different. So instead of putting a constant, a variable that represents a constant, we're going to put a linear term that may represent one or two values that are missing. For instance, if I have, whatever irreducible quadratic, I can't think of an example right now, but let's say this is raised to the second power, and there's something here in the numerator. What I need to do is put an ax squared plus bx plus c, and then another ax squared plus bx plus c, but this time squared. And now on the top, instead of just putting a or b or c, we're going to need to put ax plus b. So for the other one, it would be cx plus d, or whichever notation system you choose to use. Important thing is to be able to differentiate a linear term from an irreducible quadratic, and just so you know which numerator has to be used. That's very important. And then the next step would obviously be to find out what a, b, c, and d are. So let's look at our first example. 1 over x squared minus 5x plus 6. We want to expand this fraction. So there's always 3 steps or 3 key things I want to make sure that I look at. The first thing is I want to know, is this a proper or improper rational function or fraction? When it's proper, it means that the degree of the denominator, which in this case is 2, is higher than that of the numerator, which is true in this case. So we can go to step number 2. By the way, if it's improper, you need to use either long division or synthetic division. Anyway, step 2 involves looking at the denominator and see if we can factor it out. So for instance, this denominator, we can actually factor it out. If we put 2 parentheses, we have an x squared, so an x for each parentheses. We have a minus plus, which is minus minus, and then 3 times 2 is 6. 3 plus 2 is 5. So that's how you factor that out. By the way, before I move on, how do I know which signs go into the factorization quickly? Basically, I memorized this from high school, all the combinations. So whenever I have a plus plus on the left hand side, when I factor it out, I'm also going to have a plus plus. If I have a plus minus, I'm going to have a plus minus. If I have minus minus, then it's going to be plus minus. And finally, minus plus is always going to be minus minus. So keep that in mind. May be useful for the future. Now, I am ready to finish step 2 because these 2 linear terms, I cannot factor them any further. So I can go to step number 3, which is basically to expand the fraction. Since we have 2 linear terms, we only have to apply, as you can see here, constants. Since there's 2 terms, I'm going to have an a over x minus 3 plus, and I'll put a b over x minus 2. Now our next step would be to find out what a and b are, and we are finished. How do I do that? Well, the first thing I do is I do the smiley face to add both fractions. So I'm getting a times x minus 2, and I'm not gonna distribute them, at least yet. Then I have x minus 3 times x minus 2. And now notice this little detail. Let's call this expression 1, this expression 2, and expression 3. What I always do is I always compare my expression 1 with my expression 3, and once I find out the missing values, I take my expression number 2 as a reference for my final result. Okay, so let's do this first. What I mean by that is I'm going to say 1 equals a times x minus 2 plus b times x minus 3. Notice that the denominators for both expressions cancel out, so I don't have to write them. And now I have to find what a and b are. This is going to be really easy because I can just substitute or plug in values for x in order to achieve this. So let's say that x is equal to 3, and what's going to happen there is that the b is going to cancel, and I'm going to be left off with 1 equals a times 3 minus 2, which is 1, and therefore a is equal to 1. And now with this value, I can substitute that into my equation and find b, or I can do another value for x, which is what I'm going to do. Let's say x equals 2. What happens there is that a gets canceled, and then I have b. 2 minus 3 is minus 1, which means that b must be equal to minus 1. And now that I have my a and b values, I am ready to look at expression number 2, which is this one, and write my final result. Therefore, I can say that 1 over x squared minus 5x plus 6 can be decomposed into 1, which is a, over x minus 3, plus, and then b is minus 1, so I'm going to say minus 1 over x minus 2, and we're done. Let's do another example.